Welcome to this talk. The title is A Journey to the Post-Quantum Cryptography, and I think this is the last talk in today's session, last faculty talk. So I will go very informal, very slow, just like stories. You can see multiple buzzwords over here, post-quantum cryptography. So how many of you have heard of the word cryptography? Please raise your hands. Wow, great, good number. And how many of you know what is post-quantum? Still good number, very good. So let me first introduce myself. You can match me with the picture. So I'm an assistant professor in this department, recently joined, and my broad research area is hardware security and cryptography. I'm not a theoretical cryptographer. So what I do, I break crypto system in real life when it is running on some device and extract their secret key. And I also sometimes fix them, but I don't like to fix, I like to attack more. This talk is not on a quantum computing, okay? So I'm not going to talk on nice quantum computers and all. This talk is on cryptography, which will withstand attacks from quantum computer. So those who know cryptography, but still just a recap, that in cryptography the classical model is something like this. There are two persons, Alice and Bob, they want to communicate, and say Alice is sitting in Miami and Bob is sitting in Mayapur. So they have to use some communication channel and they don't want anybody to read that message, okay. So what they will do, they will have two set of algorithms, some magic algorithms, and they have secrets. So the secrets are shared between them, and based on the secret, Alice will encode, or we call it encrypt, his message and then send, and only Bob can decrypt the message or decode the message and read it. That's the main premise of cryptography. Now what is special about that it is not an ad hoc thing, it's not an art, it's a science, it's a science. So what we do, we give some mathematical guarantees that okay, nobody can break it. So how do we give the mathematical guarantee? I will come back to that, but before that I would like to mention that whatever is going on in this room is involving some form of cryptography. If some of you are doing WhatsApp, that's end-to-end encrypted right now, okay. So cryptography is very important at this point, and so crucial that not only our nation states and governments, but all the big companies these days, like you think of Amazon, starting from Google, everybody is investing quite a huge amount in developing this subject. So it's a very exciting subject actually. So coming back to the mathematical guarantee, so everything starts from there. So we argue the cryptographic security in this sense, that if you can break my crypto system, my algorithm, then you can solve some hard problem, okay. And hard problem means it's really hard. We do not know a polytime algorithm for that problem in computer science, it's that much hard. So yeah, if you can break that, my crypto system in some sense, you might get a Turing award because you will be solving a hard problem in that case. So like that. So therefore you can assume, you can understand that this system is pretty secure because these hard problems are being studied for years, centuries in some cases, okay. So you can say that they are pretty hard. Now again, coming back to just what cryptography does, so it does very basic things. There are two paradigms. One is, it's called symmetric cryptography. There both sides are sharing the same secret key, same secret material, okay. And another one is public key cryptography. It's a bit unique because one party generates two keys, one public key and one secret key. He keeps the secret key with him, like here Bob is keeping the secret key with himself, and he distributes the public key. So if somebody like Alice or somebody else even try to send a message to Bob, which he intends only Bob can read and nobody can read, he will just encrypt the message with a public key and send it to Bob, and Bob can decrypt the message, okay. So only Bob is able to decrypt, but everybody is able to encrypt. That is the premise. So it's clear, I hope, to everybody. Now, both symmetric cryptography and public key cryptography are based on some form of hard problems or hard problem assumption, better to say, because nobody knows whether they are really hard or not. It's just we have not been able to solve them yet. But symmetric cryptography has a different set of hardness assumption, and public key cryptography has more number theoretic or mathematically established assumptions of hard, number theoretic assumptions. So whatever is used today, most of the public key are based on two classical algorithms. One is RSA and one is elliptical cryptography. If you see RSA, although it's a bit of sweeping statement, but you can say that RSA is based on one hardness assumption, that is you cannot factor large integers. Okay. Say I am a person, I have two prime numbers, somehow I figured out two big prime numbers, I just multiplied them and I give you the n. Okay. And I ask you, can you factorize n and get me p and q? That's a terribly hard problem actually. Okay, that's pretty hard. And it is known from like years or centuries. Another form of cryptography, that is elliptic curve cryptography, which is vastly used in modern internet. So you can ignore the fact what is elliptic, what is curve for now, but let's see the problem. It's called elliptic curve discrete logarithm problem. The problem is that again you are given q and p. They are two different things, and where q equals to x into p, it's a multiplication, and you have been asked to find out x. It is also known to be a very hard problem. Okay, and q or p are basically points on the elliptic curve. So elliptic curve is a very weird looking mathematical object, and again we make it more weird by defining it on a finite field or ring. Then this is very hard problem. It becomes very hard problem, even hard to describe, you can see, and actually it's a hard problem. Okay, cut to 2025. So these things are there for like how many? 30 years from now? Yeah, 30 years. So now my question is that, are these assumptions still valid? This hardness assumptions still valid? The answer is indeed they are, but depends on your viewpoint or your computing power rather. Okay. So in 1994, a person, a very great scientist from AT&T Bell Lab, came up with an algorithm, which is one of the first quantum algorithms described so far, and he showed that he can solve the factorization problem for a prime n in order of log n cube time. Yeah. Now it's, I think there is a slightly better algorithm, but this is kind of well known. I think in 3 or 5 years, they came up with another algorithm for solving discrete logarithm under the same principle actually. Now see the change here. So here you can solve it in order of log n cube time. So n is the number, it's not the size of the number, it's the number. And otherwise with a classical computer you can solve the same problem, you can try to solve the same problem, the complexity is sub-exponential. So typically with classical computer you cannot break this kind of factorization, so you cannot break RSA, and with quantum computers you can break it extremely efficiently. That is the perspective. And then ECC is also broken. Okay. So what does that mean? That means whatever you are doing now, okay, you are not secure. If the quantum computer arrives, whatever you are doing right now will be broken and everybody can read your message, whatever you have done so far. Okay, so be careful. Now coming back to the reality again, this was theory, brilliant, beautiful theory. But where the quantum computers are now at this point. Right now, I think in 2025, please correct me if I am wrong, if there is some quantum expert here. I think IBM Condor has the highest number of qubits, 1121 qubits. But now the question is that for breaking practical RSA that are used in internet these days, how many qubits you require? The answer is you require millions of qubits actually, and we are still not there. And why millions of qubits? Because basically RSA, modern RSA that are used in internet is either 1024 bit prime or it's 2048 bit primes. It's pretty hard to break. But why millions of bits? Because quantum computation is, I mean, qubits are not perfect, they are erroneous. So you need a whole lot of error correction. For that you need extra qubits. So it becomes quite a millions of qubits. But you might say that, okay, I mean, that will be reached like after 30 years, 40 years, or I don't know when. But the estimation right now, the way quantum computing is progressing is 2019 to 2025 and all, NIST, the National Institute of Standard Technology in US, they predict that by 2030 or 2035 we will reach that capability. So actually we are in danger. Now again you might say that why do we need to bother about right now, right? We are still in a safe world. And should we really bother about spending millions and billions of dollars behind, developing some quantum resistant cryptography and all? That's a prudent question. The answer is that it is the time. Why? Let me give you a very small example of attack. Say there is some rogue government or maybe a rogue person who is simply, getting a lot of data, encrypted data from internet and simply storing it in his Google Drive or some space, okay? When the computer arrives, he readily decrypts that and then he can blackmail the entire world almost. This is a huge possibility and people are scared about that. So, those who know George Orwell, so there was a famous quote by George Orwell, those who control the past control the future. So, that's it basically. You can control the future in some sense. Another possibility is that there is some cryptographic application called digital signatures. So, in digital signatures, you are a person who signs something and nobody can forge that signature typically. Okay. So, since nobody can forge that signature, then yeah, I mean, you cannot forge a document or you cannot bluff somebody, right? But when the quantum computer arrives, you can forge all the classical signatures. So, that is a big trouble, big trouble that you can. Now, the question is that our things are doomed, but do we have a solution to that? And we have something. So, you see, you observe that the problem is basically not from the cryptographic construction side, it is the problem of the hard problems, because hard problems are broken, that is why your cryptography is doomed. So, why not search for new hard problems? Okay. So, searching for new hard problem is again a hard problem, I would say, not that hard, but hard. So, why? Because in cryptography, so those who are familiar with hard problems, they might think, okay, I will pick any NP complete problem and work, right? But the problem is that you cannot work with that. So, NP complete problems mostly bother about worst case hardness, but here you need average case hardness, that is the first point. Secondly, you need something called a trapdoor. So, the problem should be easily solvable in one side and hard to solve in the other side. So, for example, if you take the factorization like multiplication is very easy, right? But reversing the multiplication, factoring is hard. So, you need this kind of a property, it is called a trapdoor. So, not every problem gives you a trapdoor, and then these problems are typically not NP complete, they are NP intersection co-NP in some sense, but that is okay. Fortunately, we have a lot of such very interesting, very nice hard problems, which are quantum hard in fact, okay. So, there is a cohort of this problem, and for every problem we have nice algorithms from the community. Using this hard problem, if we can construct our crypto, we will be remain secure in the quantum. So, in this talk, for the sake of time, I will only talk briefly about this first problem, lattice-based crypto, and there is a reason why I am talking about lattice-based crypto, because in 2016 NIST started the competition for standardizing the post-quantum cryptography, and you know, like whatever NIST says, I mean, after that the entire world will follow that. So, very recently in 2023, they have selected the first cohort of algorithms, okay, and they are still selecting. 5 days back they standardized another one, but the first set of algorithms which are the most popular is crystals Kyber and crystals dilithium. They are both lattice based algorithm. One is for signature and one is for public key cryptography, or we call it KEM. There are other variants, but these are the most popular ones. So, it makes sense to learn a bit about lattice-based crypto. And just before going to the math, let me tell you how the world is moving towards post-quantum crypto. This slide explains that. So, you can see, you can find out the logo for every big guy over here. See, everybody is investing hugely, because within 4 to 5 years, everybody wants the internet to only use post-quantum crypto and nothing else. That is the scenario. Now, a bit of maths. But what is a lattice? Let us just talk in form of this example. So, R is your real number field and you are considering a vector space over R. So, for that vector space you have a basis, right. Now, lattice is basically nothing but integer linear combination of the basis vectors. That is a lattice. So, that is why you can see these dots over here, because they are not continual combinations, they are integer linear combination. We talk about some problems in lattice which are hard. Say I am considering R square. So, one basis is this, right, simple basis set. Now, a lattice is basically defined like this, A0, A1, where A0 and A1 are belongs to Z, Z is my integers. So, 2, 3 is a lattice point, but 0.5, 0.1 is not a lattice point. I will talk about one very hard problem in lattice world. So, this problem is to find out the shortest non-zero vector in the lattice, okay. This is called SVP, or shortest vector problem. So, you have given a lattice, the basis and all, you have to find out the shortest vector in that lattice, and it's really a hard problem, because you have to find out a very specific integer combination of the vectors. So, now it turns out that even the approximate version of this problem is also hard in many situations, which is called, which I denote as SVP gamma. So, it says that you do not need to find out the shortest vector, but you find out a vector which is at least gamma times the shortest vector, where gamma is not. So, now all these problems are kind of very hard, because proves that this SVP is an NP hard problem and all. Okay, SVP has instances where you can like you are not directly use SVP in some sense. You have some variants of that. This SVP is mostly used to prove the hardness. I mean, we actually use LWE or some gap versions of SVP and like that. But there are crypto systems where you can construct a trapdoor based on SVP. So sometimes the trapdoor is not very apparent. You have to construct that in there. So that was about SVP. I do not have much time to talk about that. But now this is the problem which we all are very proud about. This is the LWE problem on learning with errors. This is everybody acknowledges that this is the problem in theory. So the problem is very simply stated. You just sample a random matrix from somewhere there is some space from where you just sample this random matrix. Basically we do it from some finite ring, and then you also sample your secret. Okay, that is a vector. So this vector is your secret. In cryptography, the secret key, this vector represents the secret. Along with that, you also sample something else. You sample a vector of errors. So we call it errors. So these are also values. The only condition is that these values has to be drawn from a specific distribution, most of the time a normal distribution, and these values has to be small. Okay, it should not be very large, and then you just write down AS plus B, simple linear system you form, right? So let's take an example here. So this is the system what look like. It's a system of linear equations, nothing about that. But the only nice fact is that it's approximately equal to 8, not exactly equal to 8, because you have added some error. Now what's happening here? The error comes from some very specific distribution, normal discrete Gaussian distribution or some bell curve like distribution you can use, and the distribution has certain standard deviation, parameter based things and all. Okay, but the guarantee is that you cannot solve this system of equation in the presence of noise. You cannot figure out S by solving this equation. Even if I give you like several equations, if the system is highly overdefined, still you cannot solve it. And there is a mathematical proof for that. Okay, and if you just try to get the intuition is that because you have some noise over there, so what do? You use some Gaussian elimination, right? So if you are trying to use the Gaussian elimination, the noise also gets combined and all. So basically it amplifies instead of getting reduced. So that's why you cannot solve this system. And I mean, this is the problem that he used these days. Okay. Now let's see how to do cryptography using this thing. Very simple. So what was my system? My system was AS plus E equals to B, right? Where S is the secret and E is also some form of secret, but you can ignore that for the time being. Basically, you are doing the cryptography based on the secrecy of S. Okay. Now, what do you do while you are trying to make the cryptography from here is something like this. You randomly sample A, it's a public information, just a public information, and Alice, this party, has some S, which is secret information. Now, Bob, who is actually going to compute with the public key, is actually going to encrypt with the public key and send it to Alice. What he will do, he will generate a random bit string, okay, and he also has A, he knows A. Now, what Alice will do, he will generate a B transpose, another vector, which is basically S transpose into A plus E. This is exactly the hardness equation that you have solved. Like this is, so basically if somebody says that can you find out S from this equation, you cannot, because it's a lattice problem. So this is the public key of your crypto system. Okay. Now what Bob does very simple thing. He just simply multiplies A into X, sends to Alice, and based on B, he also creates something, and this is the bit he wants to send to Alice. Okay. Say for the time being, he just wants to send a single bit to Alice. Okay. So he just encrypts the bit in this way and sends to Alice. What Alice does, Alice has this U dash got from Bob. He knows S and he also knows U, which has been sent by Bob. He simply does U dash minus S transpose U, which is approximately equals to bit into Q by 2. So Q is a scaling factor basically. Okay, so let's just see this equation. It's very simple. So if you do U dash minus S transpose U, basically everything cancels out and you are left with this. Now here I told you initially error is small, right? So that's why this factor is very small. Okay. So then if bit is 0, then you are going to get an output close to q by 2. Q is a number, okay, in the integer number. You are going to get output close to q by 2, and if b is 0, you are going to get an output very close to 0. So from there you can easily understand, okay, I have got received bit 0 or bit 1, okay. So that's simply the crypto system. And now Kyber, okay, is typically based on this simple idea. Okay, there are few things that I completely skipped, like there are terms like module, LW and all. So there are more mathematical structures hidden inside, but everything depends on this very simple looking algorithm. You can form this, use this concept, and then form this Kyber algorithm. So these are the noise parameter, compression parameters and all. So this is something what we are talking about. So there are kind of three variants: 512, 768 and 1024, and there are some parameters according to that, the noise and everything, the size of the parameter, secret keys and everything, so they change. But these are just parameters. I mean, the mathematics has already been explained, it's pretty simple actually. And people came up with these three algorithms. Now, do you think you are secure? You have Kyber, the post-quantum secure algorithm. So what is your point? Like, are you really secure? Unfortunately, you are not. That's more like a buzzword, but even real life you are not. Let me show you why you are not. So, this picture abhi baki hai. So far we are talking about the mathematical security, but you have to code it down in some computer, right? You have to write a C or Python or some Verilog code. But when you write it and it is running in some system, whether in your cloud system or in your smart card or anywhere, physics comes in picture, okay. So timing is there, so you can measure the timing of the computation, the adversary, you mean the adversary. You can measure the power consumption of the computation. So say you have a smart card which is running Kyber, and you just went to some shop and put the smart card in the payment gateway, right? And you don't know who has put the payment gateway over there. So that payment gateway can measure your power consumption and break your Kyber within few seconds actually. It can do faults. So all these kind of channels we call as side channels or physical channels, and they are the threat to cryptography. So after you develop all the mathematics, you have to take care of these things, and these are big at this point. So almost every week you see this kind of things happening, and you can see like Tesla got hacked by K11 researcher 2 times, okay, and they break their authentication scheme actually, real life. You can see the video, it's in internet. And every company like Intel to AMD, they are scared of this kind of research, because whenever something happens, they have to go and fix their hardware. And whenever they release some new hardware, within 6 months, that hardware is hacked, okay. So that is the current scenario. So when cryptography, you want to run your cryptography in this, what should I say, adversarial world, you have to be very careful. And I won't go in details, but I do this kind of thing. So this is this figure is from one of my paper published last year in Chess. Chess is the biggest conference in our area. So what do you mean by attack? By attack, we mean that you can extract the secret key, first of all, and the mathematics that you have shown for Kyber, that is actually pretty good actually, that doesn't create any problem. But the problem is basically, it's your physics which ruins your nice maths, okay. But when you try to do these attacks are not only like you are just reading out the key from the device, okay. It is basically you are getting some signal from the device, which you have to analyze mathematically using the mathematics of Kyber that you have seen so far in a rough sense, and then only you can recover this kind of secret. And the point is that you can do this for everything. I mean, starting from Intel AMD to FPGAs to ASIC chips to small microcontrollers, for everything you can do these things in real life. And if you want to fix this, that's a really big issue, because doing an attack is something, but fixing is something. And what we have seen so far, the fixing, you have to go back to the mathematics. You have to go back to the mathematics. There are something called secret sharing, which is also cryptography. Using those kind of concepts, you can fix this kind of thing, okay, this kind of attack. But yeah, that is a whole, hot area of research kind of, because post-quantum algorithms have just been released, and we are looking into it big time at this. So this is our lab. Right now we have 2 people, but more people are joining, and we do all this kind of nice stuff. So we have hardware for doing that. So we practically break the algorithms and fix them. So cryptography is a great thing. We fixed the world even before the quantum computers really arrived. But then unless you take proper care in implementation, it's really futile, okay? And implementation does not mean that you code well, you code correctly or not. It's basically more to that. So you have to, do some kind of mathematics and then implement that mathematics also properly. So whole lot of exciting things running over there. So with that, I would like to just acknowledge that some of the slides were taken from our previous teacher's presentation and very nice talks on post-quantum cryptography by some, stalwarts in this area. And with that, I would like to conclude. Thank you.
Hello, sir.
Hi.
Sir, actually, normal computer can't decrypt the RSA algorithm, but for the quantum computers can do that. But we don't know actually that when it powerful quantum computer can become. So how we ensure that our algorithm that is working encrypting make sure we are in secure mode.
So the question is, are you talking about the mathematical security like with respect to the quantum computers, or you are talking about the physical security, just which one?
Mathematical way.
Mathematically, it's known that it's secure. Like if you are running it on, if you are encrypting right now with RSA and you don't have a quantum computers, you are good.
But the companies like IBM is developing and working on that, and they are not means publishing that when it so much powerful computer that release.
So everybody is working on quantum computers, and like these things will happen anytime. And right now, I can say, like if you talk about IBM Condor and all, these computers are pretty powerful. And another point, like we are still relying on Shor's algorithm. Okay, Shor has given some algorithm, relying on that. Some people I know, they are working also on improving that perspective. So it might happen that the, people will come up with some better version of Shor's algorithm, which breaks quantum cryptography in lesser number of qubits. We do not know that yet. So we do not know many things actually, but we cannot take the risk. That is the main point.
But there may be some vulnerabilities in the code itself, like developers are doing encryption algorithm. So
no,
how
there
to
is
ensure?
No vulnerability in code. We are not assuming any vulnerability in code. Code is perfect. That we are saying. So if you are talking about this physical security, that we don't assume that the code is vulnerable or anything. Everything is perfect, but still the physics actually leak some information here and there, and from there and doing some mathematical cryptanalysis, you can recover whatever you want. So that is the assumption.
Sir, in RIGEP's public key crypto system, RIGEP's, RIGEP's, sir. The lattice-based public key crypto system.
I am not heard about that. I'm not aware about that. But
sir, in your slide page number 25, it was.
Okay. So it's on my slides probably. This one? RIGEP.
Oh, yeah, RIGEP. Okay. Yeah, sorry.
Yeah.
So how do we decide the bit should be 1 if the value is close to q by 2?
Like so
how close?
Yes. How close is basically like I showed you, right, in the next slide. Here. So it's E transpose X plus bit into q by 2. So let's say the bit is 1. Okay, let's assume the bit is 1. So this value will be q by 2 plus some error, right? Plus some error. And that error is basically a small range. Okay, so what you do basically, you do some kind of quantization there. So if the error is very big, you cannot recover the secret. But since it's like, you can imagine it like this, you have a wheel and then you draw some spokes, right? So in between one spoke, your error can be there, okay? But if you take the average of that or something like that, that is your actual value. So so another way of looking into this is that this will be stored in some register when you are decrypting it, some 32-bit register or 64-bit register. You can simply drop the last few bits from the register. That will be the error. And after that, whatever you get, that is probably equals to q by 2 or something, and that is your secret.
Yes, sir. One more. I want to know from you that how the Shor's algorithm is able to crack this public key system that is based on integer factorization and discrete log.
Okay, so you are asking that how Shor's algorithm works?
Yes.
Okay, and so that's a very good question.
Yeah, one more. And so why increasing the size of the key is not sufficient for the traditional?
Yeah, I think we can take it offline. I will take it offline. You can talk to me after this with a pen and paper.
Sir, I'm still confused. That point number 2. Like if the value is close to q by 2, then we decide the bit is 1, but otherwise it's 0. But what is the condition for otherwise? Like how close?
Otherwise means it will be, see, if the bit is 0, what will happen to this multiplication? It will be 0, right?
Yeah, only
so
the
it will be E
errors.
transpose x. So I said E is a very small value.
Okay.
So E transpose x will be a small value. You are multiplying a small value with some small value, it will be small value only. So then it will be something close to 0, say 0 point something.
Okay.
And there it will be close to q by 2. So say q by q, say let's say q is 10, okay? So it will be close to 5, like that. So if it is close to 5 or close to 0, you can easily distinguish, isn't it?
Since companies are building the quantum computers, are they also working on developing algorithms that will make our data secure? For example, because quantum computers are not only for breaking the security, right? Their usage is varied. So like if the companies like IBM and all those, if they are working on building those computers, so is it legal for them to build such computers that will endanger the security of the almost the whole world?
Okay, so you are right that quantum computers might have many applications, but right now we do not know much applications of that. So in terms of legality, so there is one point, it's science. So you should not always think about what is legal and what is not. You are not going to attack somebody. Is just doing mathematics and physics, it's good, right? So it was also not legal to make an atom bomb in that case, but we made it. It's like that. And secondly, yeah, I mean, quantum computers are being researched. At the same time, we are also building this post-quantum crypto, right? And we have standardized it. We are going to replace everything by that. So in research, whenever such a threat looms, we try to find out a fix. So that's how research progresses, and that's what is happening right now.
Does this also increase like the number of people who might be needed in the workforce related to computer security and data security?
Yeah, definitely. We are badly lacking people who, wants to jump into mathematics or wants to jump into this kind of physical security field. We need a lot of people in that at this part. Otherwise, there is always some kind of vulnerability looming around. It is just you who can figure it out, and once you figure it out, then it's public. So it is there. Somebody has to figure it out. So more people we make it involved, we make our world a better place in that sense.
Okay, thank you.
So, sir, how does this compare with relatively trivial algorithms, key distribution algorithms such as BB84? So, we could have the classical implementation of sharing the same bits but via quantum channels.
So I'm not very much aware about the quantum information processing and all. Sorry about that. But yeah, I mean, this is a different subject altogether. I'm not talking about quantum key distribution and all these things here. It's more about the cryptography.
All right.
So comparison, these are two, like apple and watermelon actually.
Public key cryptography like RSA and all are used in very critical applications like banking, finance, and so what do you think that by what timeline these institutions must migrate to the post-quantum cryptography?
Right now. And they are doing it. Like for example, I'm not sure about banks, but I know, like if you take the example of Apple, NVIDIA has recently brought a post-quantum secure, library for doing post-quantum crypto on GPUs. And then if you see Apple, they have already included PQC in their E2E. There is something called Apple Talk or something, right? There's an app, like WhatsApp in Apple. So they have already included KBER in that.
Okay, so are there any such guidelines from the regulators or the law enforcement agencies that post-quantum cryptography should be implemented by which date?
So when NIST standardized it, it is kind of implied. So NIST is not going to say you that you have to do it, otherwise I will put you in jail. But it has been done, so people are now migrating quite massively.
But in India, anybody has some imposed this thing that yes, by this timeline.
India started this NQM, right? National Quantum Mission or something. So under the government, so they have started already doing that thing, and like few of us are already working in this area. So researchers are there, and I had talks to some government body, DSCI people and all, and everybody is basically moving towards that. So in fact, there was some talk, I remember people were saying that should we also run our own PQC competition, like Korea is doing that already, Korea, China, everybody is doing that. But yeah, it's still in ground level, but we are aware, at least people have started working.
Hello, sir. Recently, North Korean hacking group called Lazarus hacked Bybit's cold wallets, and they don't even use the supercomputers. They use some other method. So, and it was a multi-million-dollar attack. It was like $1.13 billion attack. So, like groups like North Korean groups and Russian groups are not even using supercomputers, and still these massive scale attacks are executing in the world. So, like, what do you say about that?
You see the slide. This is the thing. Like all of these are billion-dollar business. So probably North Korea, they haven't told you how they do it, but the thing is, I suspect what I say from there, they must have done some kind of this kind of hack.
But sir, cold wallets are like one of the hardest wallets to hack because they are offline, but still they got hacked.
See, I mean, this hardness thing, I mean, it's not cryptographic hardness we are talking about, that hardest wallet to break and all. These are kind of, unless you try it, you don't know how hard is that. Everybody will tell you before selling it that I have the best security in the world. Okay,
Yes, sir.
but then, like, if you see these attacks, especially which are happening on this Elon Musk Starlink system, or I don't take his name for the time being, or
Yes.
Tesla tests their car like anything, okay, and still send it to some university, some students will hack it. So it's
Okay.
all about, it's a cat and mouse game. So if you think that, okay, how they have breaked in and all, there are intelligent people who broke it. That's it.
Okay. Thank you, sir.
Thank you, Professor. I request Professor Sujoy to give away the token of appreciation.
Thank you.